This is the review for chapter 16 and 17. And we've got here three questions that all relate to our three choices up here. So first of all, let's just do a quick review of acids and bases. An Arrhenius base or an Arrhenius acid. First of all, let's talk about an Arrhenius acid. It's something that when you put it in water, it creates hydrogen ions, again, in water. An Arrhenius base is something that creates hydroxide ions when put in water. A Bronsted acid is a hydrogen ion, or sometimes we just call it a proton donor, something that will give its hydrogen away. A Bronsted base is a hydrogen ion, or again a proton acceptor. And then Lewis acids and bases have to do with electrons. So anytime you're talking about electron pairs in terms of acids and bases, it'll be a Lewis acid or a base. So a Lewis acid, again, acid starts with A. That is the electron pair acceptor. And the Lewis base, therefore, must be the electron pair donor. So if we understand that concept, these three questions should be fairly simple. In the reaction BF3 plus NF3 to make BF3NH3, the BF3 acts as a what? We have to think about what BF3 looks like. BF3 has 3 bonds, no non-bonding pairs. NH3 has the 1 lone electron pair and then the 3 bonds. When they react, we can see that the BF3 and the NH3 form a bond. So these 2 electrons here form a bond right here with this boron. So you have an NB bond, and then you've still got your fluorines on here and your hydrogens on here. So you can see that to form that bond, the nitrogen donated a pair of electrons. So in that case, the NH3, because it donated the 2 electrons to form the bond here, that is a classic Lewis base in that it donated the electron pair. Boron, in order to form that bond, had to be an electron pair acceptor, so therefore number 1 is D. It is a Lewis acid because the boron accepted that electron pair. Question number 2. Here's our reaction, bicarbonate and a hydroxide making carbonate and water. They want to know what are the bicarbonate and the water acting as in this reaction. Well, here's the bicarbonate. What happens to it? It goes from being HCO3 minus to just CO3 minus. So you can tell that it loses, or what we say donates, a hydrogen. What does the water do? Well, here's the water. What does it do when it goes back this way? It donates a hydrogen. So they're both donating a hydrogen. The bicarbonate becomes carbonate and the water becomes a hydroxide ion. So in both cases they're losing a hydrogen, which is donating a hydrogen. Therefore, as we can see, that's what a Bronsted acid is a hydrogen ion donor. And then E3, an electron pair donor, is called an electron pair donor. We just talked about that. Is a Lewis base. That is letter E. Question number 4. What is the pH of a 0.3 molar ammonia solution? So first of all, ammonia is NH3. When you put that in water, again, you can show the water, not show the water. You're going to get NH4 plus and you're going to get OH minus. So what is the pH of that? Well, if we make an ice table, we're going to have the original concentration of NH3 is 0.300. The water doesn't matter. The NH4 plus is 0 and 0 initially. We know that the Kb for this reaction is 1.8 times 10 to the minus fifth. So it's going to be 1.8 times 10 to the minus fifth times the concentration of NH4 plus. So that's going to be plus X minus X. Because remember, anytime you know the Ka or the Kb or Ksp or whatever it is, you're going to have an unknown variable in your ICE table. So that's why I kind of stopped after my initials and I made sure, okay, I know Kb, so if I do, that means that something in here has to be unknown. So obviously we didn't know any equilibrium, we didn't know any changes, so we have all x's here. So 1.8 times 10 to the minus fifth is going to equal x squared, which is, again, this times that, over 0.300. So then we're going to take our calculator, and I'm going to go 1.8 times 10 to the minus fifth times 0.3. I'm going to get an answer, and then I'm going to take the square root of that answer. 2.32 times 10 to the minus third is what I get, and that equals x, which is again is equal to the hydroxide ion concentration. Again, we're looking for the pH. So one thing I can do with the hydroxide ion concentration is I can get the pOH. We know that the pOH is the negative log of the hydroxide ion concentration, so it's the negative log of that number. So negative log of that answer equals 2.64, let's say. And again, I'm just writing these down, but the actual numbers I'm leaving on my calculator. And then I know to go from pOH to pH, I've got to go the pH equals 14 minus the pOH, so 14 minus whatever's on my calculator screen. So 14 minus that answer equals 11.36619, whatever. So my closest answer to that obviously is C, 11.36. Now, on the AP exam, remember now they wouldn't let you use a calculator, so this is certainly from an exam where they did let you use a calculator. What they would do is they would have something similar to that, where they would either just have the setup, where you wouldn't actually have to answer the question, but certainly on your exam coming up, something that you should be familiar with. Okay, number 5, and the reaction represented above the Ka value is 4.6 times 10 to the negative fourth, and therefore they want to know, just using that information, what the stronger base is. Remember that if the equilibrium constant is greater than 1, so K is greater than 1, that the reaction lies to the right, which means you have mostly products. Okay? If that is correct, then remember, the stronger the acid, the more it dissociates. So our two acids here are acetic acid, because again, you can see that it donates its hydrogen, and then this H3O going this way donates its hydrogen. So our two acids are acetic acid or the hydronium ion, which is at H3O+. And I don't know if we've ever mentioned that or not before, but H3O+ is something that we call the hydronium ion. Many times it's just written as H+. So if K is greater than 1, then you have mostly products, which means that acetic acid would be a stronger acid than hydronium, because again, the reaction would lie mostly to the right. If K is less than 1, which is what we actually have, it's much less than 1, then the reaction lies to the left, which means we have mostly reactants. And in this case, if we have mostly reactants, then that means that H3O dissociates easier than acetic acid does, which means the reaction lies this way, which means we have mostly reactants. Okay, now what that is telling us then is that H3O has to be the stronger acid. And unfortunately, that does not answer the question. The question is, which one's the stronger base? And the key is knowing that the stronger the acid is, here's its base, the weaker its base. So a strong acid produces a weak base. So if this is the weaker of the two acids, what do we know about its base is that it must be the stronger base, simply because its acid that it comes from is weaker than the other acid. So the stronger the acid, the weaker the base that it forms. So therefore our answer must be answer D, the acetate ion. Number 6, what is the percent ionization of 0.5 molar nitrous acid if the Ka is 4.5 times 10 to the negative fourth? If we look at this reaction, hopefully we're going to see that the ice table is going to look very similar to a lot of the other ones that we've done. We've got a 0.5 molar solution. We don't have any hydrogen or nitrite at this time. This is going to go up by x, down by x. So we're just going to have a very common x squared on top. The 0.50, we're going to make the assumption, we take out the minus x, and that's going to equal 4.5 times 10 to the negative fourth. To figure out the percent ionization, we have to figure out how much of this 0.50 molar nitrous acid actually dissociates. Because when they say percent ionization, they want to know how much of it ionized. So basically, how much of it is formed into products compared to how much we start with. So that's what we're trying to figure out. We're trying to figure out how much did we get so we can figure out what percent of that original amount we lost. So we're going to take 4.5 times 10 to the minus fourth, and we're going to multiply it by 0.50, and I get 2.25 times 10 to the negative fourth, and then I'm going to square root that, and I get an x value equal to 1.5 times 10 to the minus second. So that's how much of it ionized. What percent is that of our original 0.50? We just have to divide by our original concentration and then times by 100. So divide that number by 0.50, times it by 100 equals 3. So 3% of that solution ionized. So our answer is C. Number 7, which of the following would not make an effective buffer solution? A buffer solution is a solution in which you have either a weak acid and its conjugate base, such as a solution that contains HOCl and OCl minus, or I don't know, HBRO, anything that's not one of the 7 strong acids and its conjugate base. So for example, on A, you have H3PO4 as a weak acid, and is its conjugate base in there as well? Yes, it is. Once you lose the hydrogen, this is what you end up with. So that's a fantastic buffer solution. Okay, if we look down at the bottom, something very similar to it, H2PO4, again, think about it. Is it one of the 7 strong acids? Nope. So we got H2PO4, and then we'd have HPO4 2 minus. So that also is an excellent buffer solution. Okay, we've got bicarbonate here losing a hydrogen to become CO3 2 minus. So that's a good one. The only one that's in here that is not a weak acid is answer B. HClO4 is perchloric acid. That is one of your 7 strong acids that you have to know. Okay, one of the things they left out here that they could have certainly thrown in there is remember that an effective buffer solution can also be a weak base and its conjugate acid. So something like NH3 and NH4 plus. Those are perfectly, that would be a perfect buffer solution as well. It just has to be a weak acid or a weak base and then its conjugate acid or base. Okay, number 8 is a great question dealing with an acid and a base and a titration. It says a beaker contains 100 milliliters of that hypochlorous acid as shown above. The concentration's unknown. What's the Ka for that reaction? Ka is going to equal the concentration of H plus times the concentration of OCl minus times the concentration of HOCl. Couple of important things. Don't forget the charges on the ions. If you don't have them, it's wrong. Please make sure that you use square parentheses, not round parentheses. If you put H plus like this, that is incorrect, and they will mark you wrong for that. Okay, make sure that you have them as square parentheses, not the rounded ones. Okay, on B it says the solution is titrated with 0.1 molar NaOH, so we're going to add some base to it. The equivalence point is reached when you throw in 40 milliliters of the base. Okay, important point here. What does equivalence point mean? It means the moles of the acid equal the moles of the base. So if we look here, we've got our concentration of base and we've got our volume of the base. So if we take 0.100 molar, that's 0.100 moles per liter, and we multiply that by 0.040 liters, again changing our milliliters to liters there, we're going to have 0.004 moles of base. And what we know is at the equivalence point, the moles of the acid equal the moles of the base. So that means that to reach the equivalence point, you had to have 0.004 moles of base, which also means you had to have 0.004 moles of the acid, HOCl. So if we know that is our number of moles of acid, they want to know the concentration of acid. Well, they tell us that we have 100 milliliters of the acid, and they want to know the original concentration. Okay, original concentration means before you add those 40 milliliters in there. So to get concentration, we're just going to take 0.004 and divide it by 0.100, which is again 100 milliliters. So 0.004 divided by 0.1 equals 0.04 molar HOCl. And that would be your final answer there. Okay, and that's it for B. What was the original concentration of HOCl? The original concentration was 0.04 molar. C, determine the value of Ka for the reaction if the original solution. So again, we're kind of getting away from the titration part. Now again, we're talking about the original solution. So determine Ka. So we know that Ka is going to equal this up here. And they tell us the pH is 4.46. If we know the pH is 4.46, we right away can find the hydrogen ion concentration. So let's do that. If the pH equals 4.46, we know that the hydrogen ion concentration is 10 to the negative pH. So 10 to the negative 4.46 equals 3.47 times 10 to the negative fifth. So our Ka value is going to equal the hydrogen ion concentration, 3.47 times 10 to the negative fifth, times the OCl minus concentration. And if we think about an ice table, think about our reaction here. These both start here at 0. If H plus becomes 3.47 times 10 to the negative fifth, of course, so does OCl minus. So 3.47 times 10 to the negative fifth. So that's just going to end up being squared because they're both on top here. So they're squared. And then divide that by the concentration of HOCl. Oh, hey, what do you know? We just calculated that in part B. It's 0.04 molar. So we're going to take 3.47 times 10 to the negative fifth. We're going to square it. Then we're going to divide by 0.04. And I get a Ka value equal to 3.01 times 10 to the negative 8. And that would be it for part C. That's our Ka value. Okay, and then D, what percent of the HOCl molecules were ionized in the original solution? Well, the original concentration was 0.04, and we know that 3.47 times 10 to the negative fifth is the new concentration. So what percent of it ionized? Well, 3.47 times 10 to the negative fifth is how much ionized. Compare that to our original concentration, 0.04, and to get a percent, we multiply by 100. So 3.47 times 10 to the minus fifth divided by 0.04, and we're going to multiply by 100, and I get a response of 0.086, let's say 8%. So a very, very small amount actually ionized. Okay, then E, determine the concentration of OCl ions in the solution at the equivalence point. So this is a little bit tricky because C and D, they kind of shy away from the whole equivalence point and titration part. They go back to the original solution. But then E, they're right back to the titration. So let's go back to B really quickly. We know that in B, we have this reaction where we have, what was it, HOCl. So it's HOCl in equilibrium with H plus OCl minus. And then we're going to titrate it with some base. So remember, H plus OCl minus. So when you add a base, remember that you add it to both sides. So when you add hydroxide to this side, it becomes H2O. And on this side, you get OH minus. Now, according to our balanced to the data that we did in part B, we found that the base, there has to be 0.004 moles of base that react to reach the equivalence point. So that's 0.004. We also know that the moles of the base must equal the moles of the acid. So that's also 0.004. So we know that at the equivalence point, these completely run out. So these both go to 0. The water we don't care about. OCl minus initially is 0, but then it becomes, because these go down by 0.004, this is going to go up by 0.004. So at the equivalence point, the only thing you really have in that solution is 0.004 moles of OCl minus. So that's one part of our answer, is that we've got the moles, they just want to know the concentration. Well, we know that to get concentration, we just have to figure out the volume. So how much HOCl did we have? 100 milliliters. And again, that just comes from the beginning of the problem. Right here, if you could see it. 100 milliliters. And how much of the NaOH did we add? 40 milliliters. So what's our total volume? Should be 140 milliliters. So 0.140 liters. So we're going to take 0.004, divide it by 0.140, and you get 0.0286 molar. That's the concentration of OCl in the solution at the equivalence point. And now F. Calculate the pH of the solution at the equivalence point. Now here's where we have to think a little bit. What do we have at the equivalence point? Well, we just said all we have is that OCl minus. So at the equivalence point, you've got some OCl minus that's going to react with the water. That's going to produce only one thing. The only thing that can happen here is this hydrogen can come over here. So it's going to make HOCl plus OH minus. Okay, now, way back here, we calculated the Ka value. And again, that was for this reaction right here, when the acid was dissociating. Now what we have, though, is we have a base that is causing the water to dissociate. So instead of Ka, what we really need is we need Kb. So we need to remember that Ka times Kb equals 1 times 10 to the minus 14th. So if our Ka value is 3.01 times 10 to the negative 8th, then Kb is simply going to be 1 times 10 to the negative 14th divided by 3.01 times 10 to the negative 8th. And for Kb, I get 3.32 times 10 to the negative seventh. And when we do that, again, we have to do that because remember, this is not an acid associated. Remember, you're producing a base, and that's when you use Kb, not Ka. So we know that Kb is going to equal the concentration of HOCl times the concentration of OH minus over the concentration of OCl minus. Now, if we make a kind of a modified ice table here now, we can see that the concentration of OCl minus at the equivalence point we just calculated is 0.0286. So it's going to be 0.0286. The water's out, 0 and 0, minus X plus X plus X. How do I know I need to do this? Because I know the value of Kb. I just calculated it, but I think I erased it. It was 3.32 times 10 to the negative 7th. That's fun, huh? So I know I'm going to need some x's because I know the Kb value. So x 0.0286 minus x. So 3.32 times 10 to the minus 7th equals 0.0286 over x squared. Oh my gosh, I did that backwards. I'm an embarrassment to the chemistry community. X squared over 0.0286. Wow. It's been a long week, I guess. So 3.32 times 10 to the minus 7th times 0.0286. I'm going to take the square root of that to get x. And I get an x value equal to 9.74 times 10 to the negative 5th. And that's going to equal my hydroxide ion concentration. And then from there, remember, they're asking for the pH, I believe. Yeah, calculate the pH of the solution. So if I have hydroxide, now I can take the POH equals the negative log of that answer. So I get a POH of 4.0, which means the pH is simply 14 minus 4, which gives me a pH of 10. And that's my final answer, is the pH is equal to 10. Okay, and then our last one, number 9. This is dealing with KSP, so quite a jump from acids and bases. So we're going to have the KSP is equal to the concentration of Ag plus times the concentration of Br minus. B, calculate the value of Ag plus in 50 milliliters of a saturated solution. So we know KSP is 5 times 10 to the minus 13th, so 5.0 times 10 to the minus 13th is going to equal x times x. So basically we're just taking the square root of 5 times 10 to the minus 13th, and I get x equal to 7.1 times 10 to the minus 7th. And that's going to equal the concentration of Ag plus. It's also going to equal the concentration. Here it was Ag plus, and this one would be the Br minus. So they're both the same, obviously. So that would be it for part B. Part C says a 50 milliliter sample of some distilled water is added to the solution in part B. So you started with 50 milliliters, and they're adding another 50 milliliters of water. There's still some solid AgBr in the bottom. The solution's stirred. You get back to equilibrium. You still got some AgBr in there. What's the value of Ag plus greater than, less than, or equal to the one we just did in B? Hopefully you understand by now that no matter how much you add, if there's still some AgBr left in the bottom, that the concentration is going to remain the same. So it's not going to increase or decrease. It's going to remain the same. And simply because volume doesn't affect the concentration. Okay, because when you add more water, that just means that more of it can dissociate. So even though the volume is going up, so is the number of moles. So overall, the concentration doesn't change. Okay, D, calculate the volume of distilled water in liters necessary to completely dissolve a 5 gram sample of AgBr, and then they give us the molar mass. So if you don't know what else to do other than this, if they give you grams and then they give you the molar mass, then at least take your grams and convert them to moles. So 5 divided by 188 equals 0.0266. Let's see, they only have 2 significant figures here, so I'm just going to use 2. 0.027 moles of AgBr. So that's how many moles you need. Well, you know that your concentration is going to be 7.1 times 10 to the minus 7th. So the question is, how much solution do you need to get to a concentration of that 7.1 times 10 to the minus 7th? So we know the moles are 0.027. We know our concentration needs to be 7.1 times 10 to the minus 7th. The only question is, what does that volume need to be? So I've got my volume here. All I've got to solve for is I've got to solve for V. So I'm going to switch these two around. I'm going to have 7. I'm going to take 0.027 and divide it by 7.1 times 10 to the minus 7th. And I get a large number of 3.8 times 10 to the negative 4th. And that would not negative 4th, positive 4th liters. So basically about 38,000 liters is what it would take to create a solution where only 5 grams of that stuff would dissolve. So you're talking, you know, like the size of a swimming pool or something like that. That's, you know, quite a few liters. Okay, and then part E says a student mixes 10 milliliters of 1.5 molar and 2 milliliters of 5 times 10 to the negative 4th molar. What's the student going to observe? So it looks a little bit different, but really what you've got is you've got the AgNO3, which is going to dissociate into Ag+. You've got the Br-, which is this, which takes us back to our original equation, which is just the dissociation of AgBr. So really, what they're asking us is, what will the student observe? If the reaction proceeds this way, the student will observe nothing, because all that would be happening is the AgBr would be breaking apart into ions that you wouldn't be able to see anyway. If the reaction proceeds this way, then you're going to see a precipitate form. Now you have to ask yourself, how do I know which way a reaction proceeds? By calculating Q and then comparing the value of Q to KEQ. So the value of Q is going to be the concentration of Ag+ times the concentration of Br-. And when I do that, I've got to take my concentration, but then I have to consider that now I've got a larger volume because I took my 10 milliliters and I added 2 more milliliters to it. So my concentration of Ag+ is going to be 1.5 times 10 to the minus 4th times my original volume divided by the new volume, 12. And then Br- is going to be the same thing, the original volume times my original concentration, times my original volume, 2, divided by the new volume, 12. Okay, so what I'm using there is I'm just using the dilution formula. M1V1 equals M2V2, where I'm solving for the new concentration, so I'm just dividing by the new volume. Okay, when I do that, I'm going to take 1.5 times 10 to the minus 4th times 10 divided by 12, and I'm going to multiply that by 5 times 10 to the minus 4th times 2 divided by 12. And I get a Q value equal to 1.04 times 10 to the negative 8th. And then I need to compare that to my original KSP value, which was 5 times 10 to the minus 13th. So K was equal to 5 times 10 to the minus 13th. So I can see that Q, because of the only negative 8, Q is greater than KEQ. So therefore Q has got to go down to reach KQ. For Q to go down, these things have to go down. This part has to go up. The reaction has to proceed to the left. So what will the student observe? The student will observe a precipitate form. So basically you're going to start with two clear liquids and you would see that a precipitate would form there. Okay, and then the last one, the color of another salt of silver, AgI, is yellow. A student adds a solution of NaI to a solution of AgBr. After they stirring, they do see that the yellow forms. Write the chemical equation that occurred in the test tube. Now this is pretty straightforward. You've got NaI and you're reacting it with AgBr. When those react, it tells you that it turns yellow. Well, it tells you what's yellow. What is yellow? The AgI. So one of your products has to be the Ag going with the I. If that's one product, what's the other product going to be? The sodium going to the bromine, NaBr. So that would be your chemical equation for that reaction. Okay, that's it for the review.